Welcome back to the course entitled Symmetry, Stereochemistry and Applications. In the previous lecture, we were discussing about the isomerism of 1,2-disubstituted cyclohexane derivatives. So, while discussing that, we had talked about the cis isomers of 1,2-disubstituted cyclohexane derivatives. So, now let us start talking about the trans isomer. As you know, the 1,2-disubstituted compounds can have cis and trans two isomers, and we have discussed only about cis. So, let us see what happens when we have trans 1,2-dimethyl cyclohexane. So, if we draw the molecule in the chair conformation, the two methyl groups which are trans are always up and down. That means, in the chair conformation, both are either axial and otherwise both are equatorial. So, first we try to draw the mirror image of this compound, of this molecule, and see what happens. So, this molecule which was diaxial still remains diaxial as its mirror image, and then when we try to flip the diaxial conformer, what we get is this one. We get the corresponding di-equatorial So, now this is E E, and the corresponding mirror image of that E E would look like this. So, the trans isomer exists as either AA or EE form, in the chair conformation, and both belong to C2 point group, as there is a C2 axis in the molecule. So, if we number these molecules which we have generated, the 1 and 2, and here after flipping it is 3 and 4, this 1 and 2 are enantiomers. Similarly, 3 and 4 are enantiomers. So, now we need to find out which one is more stable. So, as we know that when we have methyl groups in axial position, they can interact by 1,3 diaxial interactions like that, and therefore, the AA is less stable compared to EE. So, we will always have in the solution or in the liquid state at room temperature the excess of these EE conformers, EE isomers, and this will also always exist as pairs, and therefore, it will be optically inactive, because these two cannot be resolved and we cannot separate one enantiomer from the other. So, that is why this 1,2 dimethyl cyclohexane in trans form, although will have 4 enantiomers, but since they are not resolvable at room temperature, therefore, they will be optically inactive. So, I would like you to see what happens if you have two different groups. Suppose instead of methyl groups you have one chlorine and one bromine in trans form, and see which one is more stable and all that, and then decide yourself whether they will be separable or not, whether they will be isolated and they can show optical activity or not. Now, let us try to see what happens when we have 1,3 dimethyl cyclohexane. The dimethyl cyclohexane in 1,3 position can have the cis isomer, where the 2 methyl groups are up, and if we flip the other possibility is to have both in the equatorial position. Sorry. So, this is axial axial and this is equatorial equatorial. See, I have drawn the equilibrium shifted towards di-equatorial, because when you have 2 methyl groups in the axial position, both of them will have very strong 1,3 diaxial interaction, and also the methyl and hydrogen will have diaxial interaction. So, this will be unstable, and we will always get the more stable isomer. Now, when we see the cis compound, this cis compound is a meso compound, as it has a sigma plane. If you try to see this molecule in the planar form, the cis isomer is, suppose this one, then this is the plane which exists in the molecule, that is the plane which contains the carbon in between. Let us try to draw it for your easy understanding. This is the mirror plane which bisects the molecule, and methyl are mirror. This carbon and that carbon are mirrors, and this carbon and that carbon are mirror image. Therefore, this compound is optically inactive. But when the substitutions are different, suppose you have a bromo and chloro substitution, then there is no sigma plane, no Cn where n greater than 1. Therefore, this compound is chiral and hence should be optically active. So, if you draw the mirror image of this compound, there will be a pair of enantiomers, and also this one is AA, you will have the corresponding EE isomer as well. So, if we consider the trans 1,3-dimethyl cyclohexane, you can understand that the two groups will be one, if one is axial, the other one will be equatorial. So, this isomer is termed as AE. If we draw the corresponding mirror image of this, we should get another AE isomer. Or rather, we should name it as EA. And then if we do a ring flip of this first isomer AE, what we get is this. So, this two forms 1 and 3 are called topomers. You can see that 1 and 2 are non-superimposable mirror images. So, they are enantiomers. Similarly, 2 and 3 are also enantiomers. And in the planar form, if we try to draw this trans 1,3, what we get is a C2 axis. Therefore, this molecule belongs to a point group C2. And this will be optically active and exist as a pair of enantiomers. So, please do it yourself when you have two different substitutions, suppose Cl and Br at 1,3 position in cyclohexane, what will be the possible isomers of that compound. Now, let us see this situation with 1,4-dimethyl cyclohexane. So, in the planar structure, if we draw dimethyl cyclohexane in the cis isomer or dimethyl cyclohexane in the planar form, if we draw the trans isomer, what do we see? We see that both of them have sigma plane. Therefore, they are achiral and optically inactive, right. So, let us then try to see what happens when you have two cyclohexane rings connected together. So, I am talking about a compound which essentially looks like this. So, this is called decalin. So, if we try to draw this molecule in the chair form, how it should look like is very interesting. We first draw the cyclohexane in the chair form for the first cyclohexane ring, which is this one, and then the second cyclohexane ring has to be drawn next to it. So, now this is the chair conformation of trans decalin. Why is it trans? Because if you see, these two hydrogens are trans. So, if you try to draw this trans decalin in Neumann projection by looking through this bond and this bond one after another. So, when you draw the Neumann projection, we draw 3 CC bonds which we have marked. So, on the front carbon here you have a hydrogen down, one hydrogen on the left hand side, and it is connected to the next carbon there, which has one hydrogen here and one hydrogen there. So, we draw these hydrogens like this. Now, the front carbon is connected through the middle carbon to the next carbon. So, we draw this. The back carbon is connected to this third carbon through that carbon. So, we draw these, and then this third carbon we have one hydrogen down and is connected to the other carbon like this. Similarly, the back carbon has one hydrogen up and connected to the other carbon like this. So, we have these hydrogens which are here and other two hydrogens which are those. So, this is the Neumann projection of trans decalin. So, then what is cis decalin? As usual, we should first draw the first cyclohexane and then the axial and equatorial bonds would join. So, this is the cis decalin isomer. So, now if we try to draw the Neumann projection of that, again we take these three bonds to look at it. So, from the first carbon point of view, we have two hydrogens, third is connected to carbon. Here we have one hydrogen and there is one hydrogen, like this is the second carbon in which is the bridging carbon, and then this carbon has one hydrogen down, and here one equatorial hydrogen, and the axial bond is connected to the next carbon. So, we should draw first two carbon centers and draw the corresponding hydrogens here. These are those four hydrogens in the front and back carbon. Then the front carbon is connected to this carbon here, the back carbon is connected to this carbon there. Now, what we see is that on the back carbon, the hydrogen which is top is going through a bond and goes and gets connected to a carbon there. This has the hydrogen, and also this gets connected this goes to the back carbon and this goes to the front carbon, which then has hydrogens like that. And here we have one hydrogen, which is that one. So, the four hydrogens that we have shown here are hydrogens which are present on that side. These four hydrogens are those four hydrogens at the back. So, this is the Neumann projection of cis decalin. I would like you to practice these projections yourself, then you will understand better. So, we will continue from here in the next lecture, where we will discuss about the diastereomerism in pi systems.